Right now, at this very moment, something extraordinary is happening 93 million miles away from you. A ball of fire 1 million times the size of Earth is burning at temperatures so extreme, a human language barely has words to describe them. Every single second, this cosmic furnace converts 600 million tons of hydrogen into helium, releasing more energy than humanity has produced in its entire existence, combined, multiplied by 1 billion. This is our sun. And here's the thing that should keep you up at night. It's dying. Not in some distant, abstract future that doesn't concern us. Our sun has already burned through half of its fuel. The countdown started 4.5 billion years ago. And with every passing moment, with every breath you take, our star is one step closer to the end. But what happens when the sun dies? What will become of Mercury, Venus, our own blue marble called Earth? Will anything survive? Will anything remember that we were ever here? The answer is both terrifying and strangely beautiful. Because the death of our sun isn't just an ending. It's a transformation so profound, so utterly magnificent, that once you understand it, you will never look at the sky the same way again. Tonight, we're going to witness something impossible. We're going to watch the entire life of a star, from its violent birth in a cloud of cosmic dust to its final, quiet death billions of years in the future. We're going to see our sun as no human has ever seen it before. This is the story of where we came from and where we're going. Let's begin. Welcome back to the channel. If you're new here, you've just stumbled onto something special. We explore the deepest mysteries of the universe, the questions that have haunted humanity since we first looked up at the stars and wondered what they were. Tonight's journey is one of our most ambitious yet. Over the next 2 hours, we're going to follow the complete life cycle of our sun, from its birth in a stellar nursery 5 billion years ago, to its ultimate fate as a slowly cooling ember in the darkness of space. We'll explore how ancient peoples first tried to understand the sun, worshiping it as a god, fearing it might disappear forever during eclipses. We'll follow the scientific revolution that finally revealed what the sun really is. We'll dive deep into the physics of stellar fusion. But don't worry, I promise to explain everything in simple terms. You don't need a physics degree to understand this. You just need curiosity. We'll watch the sun's birth in a collapsing cloud of hydrogen, witness its turbulent youth, understand its current middle age, and then project forward to its future. The red giant phase that will transform the inner planets. The planetary nebula that will spread its remains across light years of space. The white dwarf that will glow in the darkness for longer than the current age of the universe. This is a perfect video for pondering the big questions. Whether you're watching intently or letting it play while you drift through your thoughts, you're about to go on a cosmic journey that spans billions of years. So settle in, get comfortable, and prepare to see our nearest star in a completely new light. Let's start at the very beginning. Before we can understand the sun scientifically, we need to appreciate how humanity first encountered it. Because for most of human history, the sun wasn't a ball of gas undergoing nuclear fusion. It was something far more mysterious, something divine. Imagine yourself as a human being 50,000 years ago. You know nothing of physics or chemistry. You have no written language, no telescopes, no instruments of any kind. But you have eyes, and every single day, without fail, something miraculous happens. A great light rises in the east. It climbs across the sky, warming your skin, illuminating the world, making it possible to see, to hunt, to gather, to survive. Then it sinks in the west, and darkness falls. The temperature drops. Predators emerge. Danger lurks in every shadow. And then, just when the darkness seems permanent, the light returns. Is it any wonder that virtually every human culture has worshipped the sun? The ancient Egyptians called the sun god Ra. They believed Ra sailed across the sky each day in a great boat, then journeyed through the underworld each night, battling the serpent of chaos before being reborn at dawn. The pharaohs were considered sons of Ra, divine beings whose power flowed from the sun itself. The Greeks told the story of Helios, who drove a chariot of fire across the heavens, pulled by 4 immortal horses. When his son Phaethon tried to drive the chariot and lost control, he nearly set the earth on fire before Zeus struck him down with a thunderbolt. This myth explained everything from scorched deserts to the path of the sun across the sky. The Aztecs worshipped Huitzilopochtli, the god of sun and war. They believed the sun required human blood to continue its journey across the sky. This belief led to the ritual sacrifice of thousands of people, their hearts offered to ensure the sun would rise again. The stakes couldn't have been higher. Without the sun, all life would end. In Japan, the sun goddess Amaterasu was considered the divine ancestor of the imperial family. According to legend, she once hid in a cave, plunging the world into darkness. Only by tricking her with a mirror and a wild celebration did the other gods coax her out, restoring light to the world. These myths share a common thread. The sun was not just important, it was the most important thing in existence. Without it, there was only darkness, cold, and death. The sun was life itself. And then there were eclipses. Imagine living in a world without scientific explanation, and suddenly, in the middle of the day, the sun begins to disappear. A great darkness creeps across its face. The temperature drops. Animals behave strangely. Stars appear in the daytime sky. To ancient peoples, this must have been absolutely terrifying. The Chinese believed a dragon was devouring the sun. They would make loud noises, bang drums, and shoot arrows into the sky to frighten the dragon away. The Vikings thought 2 great wolves, Skoll and Hati, were chasing the sun and moon, and during an eclipse, one of them had finally caught its prey. In ancient India, the demon Rahu was said to have stolen a drink of the nectar of immortality. The sun and moon tattled on him, and the god Vishnu cut off his head. But because Rahu had already swallowed the nectar, his head became immortal. Now he eternally chases the sun and moon across the sky, occasionally swallowing them in revenge. But because he has no body, they always slip out through his severed neck. These stories seem quaint to us now, but they represent humanity's first attempts to understand the sun, to make sense of its behavior, to find patterns in the cosmic drama playing out above their heads. And here's the thing. Those ancient observers were paying attention. They were collecting data, even if they didn't call it that. They noticed that eclipses could be predicted. They tracked the sun's changing position on the horizon throughout the year. They built structures aligned with solstices and equinoxes. Stonehenge in England, built around 5,000 years ago, is precisely aligned with the midsummer sunrise and midwinter sunset. The builders didn't know about planetary orbits or axial tilt, but they knew enough to predict where the sun would rise on the most important days of the year. The Mayans developed a solar calendar of remarkable accuracy, able to predict eclipses centuries in advance. They tracked the sun's movement with obsessive precision, building their entire civilization around its rhythms. These ancient astronomers were scientists in spirit, if not in method. They observed, they recorded, they predicted. They just lacked the conceptual framework to understand what they were seeing. That framework would take thousands of years to develop. The ancient Greeks made the first serious attempts at scientific explanation. Around 450 BCE, the philosopher Anaxagoras proposed that the sun was not a god, but a giant ball of red-hot metal, larger than the Peloponnese Peninsula. This was a radical idea, one that got him arrested for impiety and exiled from Athens. But he was onto something. The sun was a physical object, subject to natural laws, not the whims of divine beings. Aristarchus of Samos went even further around 270 BC. He proposed that the Earth orbited the sun, not the other way around. He even tried to calculate the sun's distance and size, concluding that the sun was much larger than the Earth. His methods were crude, and his answers were wrong by a large factor, but his reasoning was sound. Unfortunately, Aristarchus's heliocentric model was rejected in favor of the geocentric model, championed by Aristotle and later codified by Ptolemy. For nearly 2,000 years, the Earth remained at the center of the cosmos in Western thought. It wasn't until the 16th century that Nicolaus Copernicus revived the heliocentric model. His book, published in 1543, placed the sun at the center of the solar system, with Earth and other planets orbiting around it. Copernicus was cautious about his revolutionary idea, delaying publication until he was on his deathbed. He had good reason for caution. The idea that Earth was not the center of everything had profound religious implications. If Earth was just another planet orbiting the sun, what did that mean for humanity's special place in God's creation? The conflict came to a head with Galileo Galilei. In 1610, Galileo turned his newly improved telescope toward the heavens and saw things no human had ever seen. He saw mountains on the moon, phases of Venus, and moons orbiting Jupiter. Each discovery undermined the old geocentric worldview. When Galileo published his findings and his support for the Copernican model, the Catholic Church pushed back. In 1633, he was tried by the Inquisition, forced to recant his views, and spent the rest of his life under house arrest. But the truth couldn't be suppressed forever. Over the following centuries, evidence for the heliocentric model became overwhelming. The sun was indeed the center of our solar system, and Earth was just one of several planets in orbit around it. But what was the sun exactly? What made it shine? This question proved surprisingly difficult to answer. In the 19th century, scientists calculated how much energy the sun must be producing to shine as brightly as it does. The numbers were staggering. If the sun were made of coal and burning chemically, it would have exhausted its fuel in a few thousand years. Clearly, chemical reactions couldn't explain the sun's power. Some scientists proposed that the sun was slowly contracting, converting gravitational energy into heat. This mechanism, called the Kelvin-Helmholtz mechanism, could power the sun for perhaps 20 or 30 million years. Better than coal, but still not long enough. By the late 19th century, geologists and biologists had established that the Earth was at least hundreds of millions of years old. The fossil record, the layers of sedimentary rock, the slow pace of evolution, all pointed to vast ages. The sun had to be at least as old as the Earth, probably older. Something was wrong. Either the sun had some unknown energy source, or our understanding of physics was incomplete. The answer came from an unexpected direction: radioactivity. In 1905, Albert Einstein published his special theory of relativity, including the famous equation E equals mc squared. This equation revealed that mass and energy were interchangeable, and that a tiny amount of mass could be converted into an enormous amount of energy. In the 1920s, physicists began to understand how this might apply to stars. Arthur Eddington proposed that the sun was powered by nuclear reactions, probably the fusion of hydrogen into helium. The temperatures and pressures in the sun's core would be extreme enough to force atomic nuclei together, releasing energy in the process. Eddington's hypothesis was confirmed over the following decades as nuclear physics matured. By the 1950s, scientists had worked out the detailed chain of reactions that power the sun. The mystery was solved. The sun was a nuclear furnace, converting mass into energy at a scale that dwarfed anything humans had ever imagined. It had been burning for billions of years and would continue for billions more. The ancient question of what makes the sun shine finally had an answer. But this answer raised new questions. If the sun was burning nuclear fuel, that fuel would eventually run out. What would happen then? What was the sun's ultimate fate? To answer these questions, we need to understand where the sun came from in the first place. We need to go back, way back, to a time before the sun existed. A time when the space now occupied by our entire solar system was nothing but a cold, dark cloud of gas and dust. Let's travel 5 billion years into the past. 5 billion years ago, the sun did not exist. In its place was something almost unimaginably different. A vast, cold cloud of gas and dust, drifting silently through the Milky Way galaxy. This cloud was called a molecular cloud, or sometimes a stellar nursery. It was composed primarily of hydrogen molecules, with traces of helium and tiny grains of cosmic dust. If you could have traveled through this cloud, you would have seen almost nothing. The gas was so thin, so diffuse, that there were only a few thousand particles per cubic centimeter. For comparison, the air you're breathing right now has about 25 quintillion particles per cubic centimeter. The cloud was essentially a vacuum by everyday standards. And it was cold, bitterly cold, about 10 to 20 degrees above absolute zero, which translates to around minus 440 degrees Fahrenheit. At those temperatures, molecules barely move. Time itself seems to slow down. This cold, dark cloud drifted through the galaxy for millions of years. Nothing happened. Nothing changed. It was the most boring place in the universe. But something was about to disturb this cosmic peace. Scientists have debated what exactly triggered the collapse of our pre-solar cloud. Several candidates have been proposed, and more than one might have played a role. One possibility is a nearby supernova, the explosive death of a massive star. When a supernova detonates, it sends shockwaves racing through space at thousands of miles per second. If such a shockwave passed through our molecular cloud, it would have compressed regions of the gas, pushing particles closer together. We actually have evidence for this scenario. Certain meteorites contain traces of short-lived radioactive elements that could only have been produced in a supernova shortly before the solar system formed. This suggests that a nearby stellar explosion might have seeded our cloud with these elements while simultaneously triggering its collapse. Another possibility is that the cloud simply reached a critical point on its own. All clouds have some internal turbulence, random swirling and churning of gas. If a denser region forms by chance, gravity can take over and start pulling more material inward. There's also evidence that our protosun formed as part of a cluster, alongside hundreds or thousands of sibling stars. The gravitational influence of forming neighbors could have helped trigger collapse. Whatever the cause, something happened about 4.6 billion years ago that set our story in motion. A region of the cloud began to contract under its own gravity. At first, the collapse was almost imperceptibly slow. The gas drifted inward at speeds of perhaps a few feet per second. But as more material accumulated at the center, gravity grew stronger. And stronger gravity meant faster collapse. This is where things get interesting. As the cloud collapsed, something unexpected happened. It started to spin. But why would a collapsing cloud start rotating? The answer is something called conservation of angular momentum. It's the same principle that makes a figure skater spin faster when she pulls her arms close to her body. The cloud had a tiny, almost unnoticeable rotation from the start, probably inherited from turbulence in the larger molecular cloud. But as the material pulled inward, that tiny rotation was amplified dramatically. Think of water draining from a bathtub. The water might be barely moving, but as it spirals down toward the drain, it speeds up and forms a visible vortex. The same thing happened with our collapsing cloud, but on a scale millions of times larger. A spinning cloud flattened into a disk. Material at the center, where most of the mass was accumulating, became the protosun. Material in the surrounding disk would eventually become the planets, moons, asteroids, and comets of our solar system. But we're getting ahead of ourselves. Let's stay focused on the center, where our sun is being born. As material continued to fall onto the protosun, the pressure at the center increased. And when you compress gas, it heats up. This is basic physics, the same reason a bicycle pump gets warm when you pump air into a tire. The gravitational energy of infalling material was being converted to thermal energy. The center of the cloud got hot, really hot. At first, the proto-sun was just a warm blob, maybe a few hundred degrees. As more material accumulated, temperatures climbed into the thousands of degrees. The proto-sun began to glow, first with infrared radiation, then with visible red light. But this wasn't a true star yet. A star is defined by nuclear fusion, and fusion hadn't started. The proto-sun was glowing from gravitational compression, not nuclear reactions. It was still just a massive ball of collapsing gas. This phase is called the protostar stage, and it lasted for a few 100,000 years. During this time, the proto-sun was still actively accreting material from the surrounding disk. It was growing larger and hotter with each passing century. And something dramatic was happening. The proto-sun was developing a personality. Young protostars are violent, chaotic objects. They spin rapidly. They have powerful magnetic fields that channel material into streams and jets. Many of them launch bipolar outflows, twin beams of material shooting out from the poles at hundreds of miles per second. If you could have visited our solar system during this time, you would have seen a chaotic scene. The proto-sun, glowing in angry red, surrounded by a swirling disk of gas and dust. Twin jets shooting outward, clearing paths through the surrounding cloud. Infant planets just beginning to form from dust grains in the disk. It was beautiful. It was violent. It was the birth of a solar system. Now you might wonder, how could we possibly know what happened so long ago? The answer is that we can see stellar birth happening right now around other stars. When astronomers point powerful telescopes at molecular clouds throughout our galaxy, they can observe stars in every stage of formation. They can see collapsing cloud cores that haven't yet ignited. They can see protostars with jets and accretion disks. They can see young stars that have just begun fusion. One of the most spectacular examples is the Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of Orion the Hunter. Through a telescope, this nebula reveals hundreds of newborn stars and protostars in various stages of development. It's like a stellar maternity ward where we can watch new suns being born. We also have physical evidence much closer to home. The oldest rocks in our solar system, found in certain meteorites, date to 4.567 billion years old. This gives us a remarkably precise timestamp for the birth of our solar system. We know when the sun formed, plus or minus a few million years. Now let's continue our story. The proto-sun kept contracting, kept heating up. Temperatures at the core climbed through millions of degrees. Pressures reached values that are almost incomprehensible, hundreds of billions of times the atmospheric pressure at Earth's surface. At some point, the core reached a critical threshold, about 10 million degrees Celsius, and corresponding extreme pressure. At these conditions, hydrogen nuclei are moving so fast and are squeezed so close together that they can overcome their natural repulsion and fuse. This is the moment of stellar ignition, the moment when our sun truly became a star. When fusion ignited in the core, it released an enormous surge of energy. This energy pushed back against the crushing force of gravity, halting the collapse. The protosun found a balance, a stable equilibrium between the inward pull of gravity and the outward pressure of fusion energy. This balance would last for billions of years. But the sun's birth wasn't over yet. It still had some growing up to do. Newly ignited stars go through a turbulent adolescence called the T-Tauri phase. During this period, which lasts a few million years, the young star is still somewhat unstable. It experiences wild fluctuations in brightness. It produces intense stellar winds that gradually blow away the remaining gas and dust from the surrounding disk. This stellar wind is crucial. It clears the solar system of leftover debris, allowing the planets to settle into stable orbits. It also terminates the period of planet formation. Once the gas is gone, no more giant planets can form. Our sun probably went through violent outbursts during its T-Tauri phase. It may have been 10 or even 100 times more active than it is today, bombarding the young planets with intense radiation and solar flares. The early Earth was certainly affected by this violent young sun, but gradually, over tens of millions of years, our star settled down. The wild fluctuations diminished. The stellar wind calmed. The sun found its rhythm. And about 4.5 billion years ago, our sun became a full-fledged main sequence star. A stable, steadily burning star in the prime of its life. This moment, the beginning of the main sequence phase, is what astronomers consider the true birth of a star. Everything before was preamble. Everything after is the star's actual lifetime. Now comes the question we've been building toward. What exactly is happening inside the sun? What keeps it burning, decade after decade, century after century, eon after eon? To understand that, we need to dive deep into the heart of the sun. We need to witness nuclear fusion up close. The core of the sun is a place beyond human imagination. If you could somehow survive the journey, descending through the visible surface, through layer after layer of increasingly dense plasma, finally reaching the core, you would find yourself in conditions that make the surface of Venus look like a pleasant vacation spot. The temperature here is about 15 million degrees Celsius. At this temperature, matter exists as plasma, a state where atoms are stripped of their electrons. Nuclei and electrons buzz around independently, colliding with violent energy. The pressure is about 250 billion times the pressure of Earth's atmosphere at sea level. And everywhere, constantly, fusion is happening. Let me explain what fusion actually is, because understanding this process is key to understanding everything about our sun. All atoms have nuclei at their center. The nucleus contains protons, which have a positive electric charge, and neutrons, which have no charge. Because protons are positively charged, they repel each other. If you tried to push two nuclei together, they naturally push apart. This electrical repulsion is fierce, and under normal conditions, nuclei never get close enough to merge. But there's another force in nature, called the strong nuclear force, that can bind nuclei together. This force is incredibly powerful, but it only works at extremely short distances, about the size of an atomic nucleus. So if you can somehow get two nuclei close enough together, the strong force takes over and they fuse into a single, heavier nucleus. The trick is getting them that close. You need extreme conditions to overcome the electrical repulsion. In the core of the Sun, those conditions exist. At 15 million degrees, hydrogen nuclei, which are just single protons, are moving at incredible speeds, hundreds of miles per second. And in the crushing density of the core, they're constantly colliding. Most collisions still result in the nuclei bouncing apart. The electrical repulsion wins. But occasionally, just occasionally, two protons manage to get close enough for the strong force to kick in. When that happens, they fuse. The primary fusion process in the Sun is called the proton-proton chain. It's a multi-step dance that converts 4 hydrogen nuclei into 1 helium nucleus. Here's how it works. First, 2 protons collide and fuse. But there's a complication. 2 protons can't stick together as a stable nucleus. Almost immediately, one of the protons transforms into a neutron through a process called beta plus decay. This releases a positron, an anti-electron, and a ghostly particle called a neutrino. What you're left with is a nucleus containing 1 proton and 1 neutron. This is called deuterium, or heavy hydrogen. Next, this deuterium nucleus collides with another proton. They fuse together, creating a nucleus with 2 protons and 1 neutron. This is helium-3, a lightweight version of helium. The reaction also releases a gamma ray, a photon of high-energy light. Finally, 2 helium-3 nuclei collide and fuse. The result is a nucleus with 2 protons and 2 neutrons, which is regular helium-4. In the process, 2 protons are released back into the plasma, free to start the cycle again. The net result? 4 protons become 1 helium nucleus, plus energy. Now here's where Einstein comes in. If you carefully measure the mass of 4 protons, and then measure the mass of 1 helium nucleus, you'll find something strange. The helium is slightly lighter than the 4 protons that made it. About 0.7% of the mass has disappeared. But mass doesn't just vanish. According to Einstein's equation, E equals mc squared, mass and energy are interchangeable. That missing 0.7% has been converted into energy. This is the source of all the Sun's power, the conversion of mass into energy through nuclear fusion. Every second, the Sun converts about 4 million tons of matter into pure energy. That might sound like a lot, but compared to the Sun's total mass of 2,000 trillion tons, it's negligible. At this rate, the Sun has enough hydrogen to keep burning for another 5 billion years. But here's something remarkable about this process. It's incredibly inefficient. I don't mean that fusion itself is inefficient. The mass-to-energy conversion is phenomenal compared to any chemical reaction. I mean that the collision rate is extremely low. For any given proton in the Sun's core, the average wait time before it successfully fuses with another proton is about 5 billion years. That's not a typo. A typical proton in the core right now has been bouncing around for billions of years without fusing, and might bounce around for billions more before it finally succeeds. The only reason the Sun produces so much energy is that there are unimaginably many protons. Even though each individual reaction is rare, The sheer number of particles means that billions of tons of hydrogen are fusing every second. This low reaction rate is actually crucial for our existence. If fusion were more efficient, the sun would burn through its fuel much faster and would have exhausted itself long before life could evolve on Earth. The universe seems to be precisely calibrated in this and many other ways to allow for the emergence of complexity. Now, what happens to all that energy once it's produced in the core? The fusion reactions release energy primarily in the form of gamma rays, high-energy photons. These photons try to travel outward, away from the core, but they don't get very far before hitting something. The core and the surrounding layers of the sun are incredibly dense. Photons travel only about a centimeter on average before being absorbed by an atom. The atom then re-emits a photon, but in a random direction. This photon travels another centimeter before being absorbed again, and so on. This process is called a random walk, and it's agonizingly slow. A photon created in the core takes, on average, about 170,000 years to reach the surface. 170,000 years. Not because the sun is that big, but because the photon keeps getting absorbed, re-emitted, absorbed, re-emitted, zigzagging randomly through the dense plasma. The light warming your skin right now carries energy that was generated in the core during the last ice age, when woolly mammoths roamed the earth and early humans were still figuring out how to survive. But there's another particle created during fusion that doesn't have this problem. Neutrinos are produced in several steps of the proton-proton chain. Unlike photons, neutrinos barely interact with matter at all. They stream outward from the core at nearly the speed of light, passing through the entire sun in about 2 seconds. Then they race across space. 8 minutes later, they reach Earth, and they pass right through our planet as if it weren't there. About 100 billion solar neutrinos pass through your thumbnail every second, and you never notice because they almost never hit anything. Detecting solar neutrinos requires enormous effort. Giant underground tanks of special fluids surrounded by thousands of sensitive detectors, waiting for the rare interaction when a neutrino actually hits an atomic nucleus. Why do we bother? Because neutrinos give us a direct window into the core of the sun. The photons we see from the sun's surface carry information about conditions at the surface. But neutrinos come straight from the core, unimpeded. By detecting solar neutrinos, we can verify that fusion is actually occurring at the rates our models predict. For many years, it was a crisis in solar neutrino physics. Detectors were seeing only about 1/3 as many neutrinos as predicted. Either our understanding of the sun was wrong, or our understanding of neutrinos was wrong. It turned out to be the neutrinos. We discovered that neutrinos come in 3 types, called flavors, and they can transform from one flavor to another as they travel. The early detectors were only sensitive to one flavor, so they were missing the others. Once we developed detectors sensitive to all flavors, the numbers matched beautifully. This discovery, confirming neutrino oscillations, earned scientists the Nobel Prize and validated our understanding of solar physics. The neutrino problem became a neutrino triumph. Now let me address something that might be confusing. If fusion releases so much energy, why doesn't the sun just explode like a hydrogen bomb? The answer is self-regulation. In a hydrogen bomb, the fusion fuel is compressed briefly by a conventional explosive. Then fusion releases all its energy in a fraction of a second. There's nothing to contain it. The result is an explosion. In the sun, gravity provides a container. The energy released by fusion creates outward pressure. Gravity pulls inward. These two forces reach an equilibrium. But here's the clever part. If fusion temporarily increases, the core heats up and expands slightly. This expansion reduces the density and temperature, which slows fusion back down. Conversely, if fusion decreases, the core contracts and heats up, which speeds fusion up again. The sun has a built-in thermostat. It's self-regulating. This is why it can burn steadily for billions of years without exploding or going out. Let me describe the sun's internal structure, because it's not just a uniform ball of hot gas. It has layers, each with distinct properties. At the very center is the core. This is where fusion happens. The core extends about 25% of the way from the center to the surface, but it contains about half of the sun's mass. Matter here is about 150 times denser than water, despite being a superhot plasma. Surrounding the core is the radiative zone. This layer extends from about 25% to about 70% of the way to the surface. Here, energy travels outward in the form of photons undergoing their random walk. It takes those 170,000 years we mentioned to cross this layer. Above the radiative zone is the convective zone, extending from 70% of the way out to the surface. Here, energy is transported differently. Instead of radiation, you get actual physical movement of hot material. Giant convection cells, like bubbles in a pot of boiling water, carry hot plasma up to the surface. The plasma releases its energy, cools down, and sinks back down. This churning motion is much faster than radiative diffusion. Finally, we reach the photosphere, what we think of as the sun's visible surface. This is where the sun becomes transparent enough for photons to escape into space. The photosphere has a temperature of about 5,500 degrees Celsius and is only about 500 kilometers thick. Above the photosphere are the chromosphere and corona, which we'll explore in a later chapter. For now, appreciate what we've learned. The sun is a nuclear reactor with a built-in thermostat, converting hydrogen into helium at a rate that has remained steady for 4.5 billion years. This stability is what made life on Earth possible, but nothing lasts forever. The sun is slowly changing, even now, and in the distant future, it will transform beyond recognition. Before we look at that future, let's take some time to appreciate the sun as it is today. When you look at the sun, assuming you're using proper eye protection, it appears as a perfect, unchanging disk of light. But this apparent simplicity is an illusion. The sun is a dynamic, ever-changing object with weather patterns, magnetic storms, and features that shift over hours, days, and years. Let's start with sunspots, perhaps the most famous features on the solar surface. If you look at the sun through a properly filtered telescope, you'll notice dark patches scattered across its face. These are sunspots, and they've been observed since ancient times. Chinese astronomers recorded sunspots over 2,000 years ago. Galileo studied them extensively with his early telescope, using them to prove that the sun rotated. But what exactly are sunspots? They're regions where the sun's magnetic field is especially strong. In these areas, the magnetic field suppresses convection, preventing hot material from rising to the surface. As a result, sunspots are cooler than their surroundings, about 3,500 degrees Celsius, compared to 5,500 degrees for the rest of the photosphere. They're still incredibly hot by any normal standard. If you could isolate a sunspot and view it against a dark background, it would glow brightly. It only appears dark because it's being compared to the even brighter surrounding photosphere. Sunspots come in all sizes. Small ones might be the size of Earth. Large ones can be bigger than Jupiter. They typically form in pairs or groups with opposite magnetic polarities, like the north and south poles of a bar magnet. Sunspots are temporary features. A typical sunspot might last a few days to a few weeks before fading away, but they're constantly forming and disappearing, so there are usually at least a few visible at any given time. The number of sunspots follows an 11-year cycle. During solar maximum, there might be over 100 sunspots visible. During solar minimum, there might be none for weeks at a time. This cycle was first discovered by a German astronomer named Samuel Schwab in 1843, after 17 years of patient observation. But the sunspot cycle isn't just about the number of spots. It also involves a strange migration pattern. At the beginning of a new cycle, sunspots tend to appear at high latitudes, about 30 to 40 degrees north and south of the solar equator. As the cycle progresses, new sunspots appear closer and closer to the equator. By the end of the cycle, spots are emerging near the equator itself. Then the cycle restarts with spots at high latitudes again. This pattern, when plotted over time, creates a distinctive butterfly-shaped diagram. Even more mysteriously, the sun's magnetic polarity flips with each cycle. If northern hemisphere sunspots have a certain polarity configuration during one cycle, they'll have the opposite configuration during the next cycle. So the full magnetic cycle is actually 22 years, not 11. What causes this cycle? The answer lies deep in the sun's interior, in a region called the tachocline. The tachocline is the boundary between the radiative zone and the convective zone. Here, different layers of the sun rotate at different speeds, creating shear. This differential rotation, combined with convective motion above, generates and amplifies magnetic fields through a process called a dynamo. The details are complex and not fully understood. Computer simulations can reproduce some features of the solar cycle, but struggle with others. Predicting the strength of future solar cycles remains difficult. Even our nearest star holds mysteries. Beyond sunspots, the sun displays more violent phenomena. Solar flares are sudden, intense bursts of radiation. They occur when magnetic field lines in active regions become tangled and suddenly reconnect, releasing enormous amounts of stored energy in minutes or even seconds. To understand magnetic reconnection, Think of a rubber band that's been twisted too far. Eventually, something has to give. The band snaps. In the sun, twisted magnetic field lines similarly snap and reconfigure, releasing their stored energy explosively. A large solar flare can release energy equivalent to billions of hydrogen bombs. This energy accelerates particles to near light speed and produces radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Most of this radiation is absorbed by Earth's atmosphere and poses no threat to us on the surface. But it can disrupt radio communications, especially on the day side of Earth. The ionosphere, the layer of charged particles high in our atmosphere that reflects radio waves, gets disturbed by the sudden influx of radiation. Even more dramatic are coronal mass ejections, or CMEs. These are massive eruptions that blast billions of tons of solar material into space. Unlike flares, which are primarily radiation events, CMEs involve actual matter, giant clouds of plasma threaded with magnetic fields. CMEs travel much slower than light, taking 1 to 3 days to reach Earth. But when they arrive, they can trigger geomagnetic storms. Earth's magnetic field normally deflects the solar wind around our planet. But when a CME arrives, especially one with a magnetic field oriented opposite to Earth's, it can connect with our magnetic field and dump energy into it. The magnetic field quivers and shakes, inducing electrical currents in anything conductive on or beneath Earth's surface. These induced currents can cause problems. Power grids can be damaged. Satellites can be disrupted or destroyed. Radio communications can go haywire. But they also produce something beautiful: auroras. Auroras, the northern and southern lights, occur when charged particles from the sun follow magnetic field lines down into Earth's atmosphere near the poles. These particles collide with atmospheric gases, exciting atoms that then emit light. Oxygen produces green and red colors. Nitrogen produces blue and purple. During a strong geomagnetic storm, auroras can be visible much farther from the poles than usual. People in the southern United States or Mediterranean Europe have occasionally seen auroras during major storms. The most powerful geomagnetic storm on record was the Curated event of 1859. A massive solar flare, visible to the naked eye, was followed by a CME that reached Earth in only 18 hours, indicating it was traveling exceptionally fast. Telegraph systems worldwide went haywire. Operators received electrical shocks. Papers in telegraph offices caught fire. Auroras were visible as far south as the Caribbean and as far north as Colombia. If a Carrington-class event hit Earth today, the consequences could be severe. Our civilization depends on electrical infrastructure in ways that 1859 could never have imagined. Power transformers could be damaged, and since large transformers can take months to replace, we could face extended blackouts affecting millions of people. Satellites could be destroyed. GPS navigation could fail. Radio communications could be disrupted. This isn't science fiction. It's a recognized risk that space agencies and power companies are actively working to address. We now have satellites monitoring the sun continuously, giving us a few hours to days of warning before a CME arrives. But our defenses are still limited. Let me now describe some features above the Sun's visible surface. The chromosphere is a thin layer just above the photosphere. It's normally invisible, outshone by the brilliant surface below. But during a total solar eclipse, when the moon blocks the photosphere, the chromosphere becomes visible as a thin reddish ring around the dark lunar disk. The red color comes from hydrogen atoms emitting light at a specific wavelength. Above the chromosphere is the corona, the Sun's outer atmosphere. The corona is visible during total solar eclipses as a pearly white halo extending millions of miles into space. It's also visible continuously using instruments called coronagras that block the bright solar disk. The corona presents one of the Sun's most perplexing mysteries. It's incredibly hot. While the photosphere is about 5,500 degrees, the corona reaches temperatures of 1 to 3 million degrees. How is that possible? If you step away from a fire, you get cooler, not hotter. So why does the Sun's outer atmosphere get hotter as you move away from the surface? Scientists have been puzzling over this coronal heating problem for decades. The most likely explanation involves a combination of small-scale magnetic explosions called nanoflares and waves traveling along magnetic field lines. These waves, similar to vibrations traveling along a guitar string, carry energy from lower layers and deposit it in the corona. Recent missions have helped us understand this mystery better. The Parker Solar Probe, launched in 2018, is venturing closer to the Sun than any spacecraft in history. At its closest approach, it passes within about 4 million miles of the solar surface, inside the orbit of Mercury. The probe is protected by a heat shield made of carbon composite materials, about 8 inches thick. Behind this shield, the spacecraft's instruments remain at room temperature, while the front of the shield endures temperatures over 2,500 degrees Fahrenheit. Parker Solar Probe has observed mysterious structures called switchbacks, S-shaped kinks in the solar magnetic field that might play a role in heating the corona. It has directly sampled the corona and solar wind. It has provided data that will keep scientists busy for years. Let me tell you about one of the most spectacular astronomical events visible from Earth: the total solar eclipse. A solar eclipse occurs when the moon passes between Earth and the Sun, blocking the solar disk. This can only happen during a new moon, when the moon is on the Sun's side of Earth. But it doesn't happen every new moon, because the moon's orbit is tilted about 5 degrees relative to Earth's orbit around the Sun. Most of the time, the moon passes above or below the Sun from our perspective. When the alignment is just right, we get a total eclipse. And here's an extraordinary coincidence. The moon and the Sun appear almost exactly the same size in our sky. The Sun is about 400 times larger than the moon, but it's also about 400 times farther away. As a result, they appear nearly the same angular size, about half a degree. This means that during a total eclipse, the moon can completely cover the bright photosphere while leaving the corona visible. The effect is stunning. The sky darkens to twilight. Stars and planets appear. The temperature drops noticeably. And around the black disk of the moon, the ghostly corona spreads like a halo of light. This won't last forever. The moon is slowly drifting away from Earth, about 1.5 inches per year. In about 600 million years, the moon will appear too small to completely cover the sun, and total eclipses will no longer be possible. We live in a fortunate era. Total eclipses have been crucial for solar science. Before coronagraphs, they were the only opportunity to study the corona. During an eclipse in 1868, astronomers observed a spectral line that didn't match any known element. They named the new element helium after Helios, the Greek god of the sun. Helium wouldn't be discovered on Earth until nearly 30 years later. Eclipses also provided one of the first confirmations of Einstein's general relativity. In 1919, astronomers photographed stars near the sun during a total eclipse. They found that the stars appeared slightly shifted from their usual positions. The sun's mass was bending space itself, deflecting the light from distant stars. This matched Einstein's predictions precisely and made him world famous. Before we leave the present-day sun, let me emphasize one remarkable fact. Despite all its activity, its sunspots and flares and coronal mass ejections, the sun's total energy output varies by only about 0.1% over the solar cycle. This extraordinary stability is what allows life to flourish on Earth. If the sun's brightness varied by even a few percent, our climate would swing wildly between extremes. We are lucky to orbit such a steady, reliable star. But steady doesn't mean unchanging. The sun is evolving, slowly but inexorably. And in the distant future, it will transform in ways that will doom the inner solar system. Let's look at what's coming. Right now, at this moment in its life cycle, our sun is in a phase called the main sequence. This is the longest and most stable phase of a star's existence, the cosmic equivalent of adulthood. During the main sequence, a star fuses hydrogen into helium in its core. The energy released creates an outward pressure that balances the inward pull of gravity. This balance keeps the star stable for billions of years. Our sun entered the main sequence about 4.5 billion years ago. It will remain on the main sequence for another 5 billion years or so. That's a total main sequence lifetime of roughly 10 billion years. During this time, the sun changes, but slowly. So slowly that it's essentially imperceptible on human timescales. Here's what's happening. In the core, hydrogen is being converted to helium. As this process continues, the composition of the core gradually changes. More helium, less hydrogen. This might seem like just an accounting detail, but it has real physical consequences. Helium nuclei are heavier than hydrogen nuclei and carry a larger electric charge. As the core becomes more helium-rich, it becomes denser. To maintain the same rate of energy production, the core must get slightly hotter. This increasing core temperature has a surprising consequence. The sun is getting brighter. Fusion rates are extremely sensitive to temperature. A small increase in core temperature produces a significant increase in fusion energy. This extra energy works its way outward, and the sun's overall luminosity increases. When the sun was young, freshly arrived on the main sequence, it was about 30% dimmer than it is today. This raises a puzzle called the faint young sun paradox. Geological evidence clearly shows that liquid water existed on Earth as far back as 4.4 billion years ago. There are ancient rocks that could only have formed in the presence of water. There are sediments that show water erosion. The early Earth was not frozen. But if the sun was so much dimmer, how was there liquid water? Shouldn't the early Earth have been a snowball? The most likely answer involves greenhouse gases. Early Earth's atmosphere was probably much richer in carbon dioxide and methane than today. These gases trap heat, raising surface temperatures even with a dimmer sun. As the sun brightened over time, Earth's climate feedback systems removed greenhouse gases from the atmosphere, keeping temperatures roughly stable. Silicate weathering, biological processes, and other mechanisms have maintained a habitable climate for billions of years. But there's a limit to how much these feedbacks can compensate. Looking forward, the sun will continue to brighten. In about 1 billion years, it will be roughly 10% brighter than today. This increase will push Earth's climate past a critical threshold. The oceans will begin to evaporate. Water vapor is a potent greenhouse gas. More water vapor means more warming, which means more evaporation. This runaway feedback loop will eventually turn Earth into a steam-choked hellscape, more like Venus than the blue marble we know. The oceans could be completely gone in about 3 billion years. Earth's surface will be baked to temperatures of several hundred degrees. And this is still during the main sequence, before the sun undergoes its dramatic transformation. 1 billion years sounds like an abstract, impossibly distant time frame. And in some ways, it is. Human civilization is about 10,000 years old. 1 billion years is 100,000 times longer than all of recorded history. But life has already existed on Earth for nearly 4 billion years. Complex life has existed for about 600 million years. 1 billion years is long, but it's not longer than the timescales of biological evolution. If life survives that long, it will need to adapt or relocate. Earth will become uninhabitable not through any sudden catastrophe, but through the slow, inexorable brightening of the sun. Now let's consider what the main sequence means in a broader context. The main sequence isn't a single type of star. It's actually a range, from small red dwarfs to large blue giants. What all main sequence stars have in common is that they're fusing hydrogen in their cores. But the mass of the star determines almost everything else. Small stars, called red dwarfs, have less than half the sun's mass. They're cool, dim, and incredibly long-lived. A red dwarf with 10% of the sun's mass could burn for 10 trillion years, nearly 1,000 times longer than our sun. No red dwarf has ever died of old age, because the universe isn't old enough. Large stars with more than about 8 solar masses are hot, bright, and short-lived. A star with 50 times the sun's mass might live for only a few million years before exploding. Our sun sits in the middle, not the smallest, not the largest, not the shortest lived, not the longest lived, almost perfectly suited for the development of complex life. Here's something to consider. If our sun were a red dwarf, it would live much longer. But red dwarfs present problems for habitability. They're so dim that a planet would need to orbit very close to receive enough warmth. At such close distances, the planet would likely be tidally locked, with one side always facing the star and the other in eternal darkness. Red dwarfs also tend to have violent flares that could strip away planetary atmospheres. If our sun were a blue giant, it would be brighter and warmer, but it wouldn't last long enough for complex life to evolve. Blue giants burn out in millions of years, not billions. Our sun appears to be in a sweet spot, bright enough to warm a planet at a reasonable distance, long-lived enough to allow billions of years of evolution, stable enough to provide consistent conditions. Is this luck? Is this selection bias, meaning we can only exist around stars suitable for our existence? Or is there something about G-type yellow dwarfs that makes them especially suited for life? We don't know yet. But as we discover more planets around different types of stars, we might begin to answer this question. For now, let's appreciate our sun's generosity. 4.5 billion years of steady, reliable energy. Another 5 billion years to go. And for about the next billion years, Earth will remain habitable. That's the good news. The less good news is what comes after. When the hydrogen in the sun's core finally runs out, everything will change. The balance that has kept our star stable for billions of years will break down, and the sun will begin its transformation into something utterly different. Let's watch it happen. 5 billion years from now, give or take, the sun will begin its transformation. The core will have accumulated so much helium that it can no longer sustain hydrogen fusion at its center. But the core won't just shut down. Instead, something more complicated happens. The helium-rich core contracts under its own weight because there's no longer enough fusion energy to push back against gravity. But this contraction heats the core, and surrounding the helium core, there's still a shell of hydrogen. When the core contracts and heats up, this hydrogen shell ignites. Shell burning is fundamentally different from core burning. The energy is produced outside the core, in a shell surrounding it. This configuration is less stable than core burning, and it has dramatic effects on the outer layers of the star. The outer layers respond to the increased energy output by expanding enormously. The sun will swell to massive proportions. Its outer boundary, currently about 430,000 miles from the center, will push outward, past the orbit of Mercury, past the orbit of Venus, perhaps reaching the current orbit of Earth. Our sun will become a red giant. The term red giant describes two key properties. Giant, because the star becomes vastly larger than a main sequence star. Red, because the expanded surface is cooler, and cooler stars appear redder. When the sun reaches its maximum size as a red giant, its radius will be about 1 astronomical unit, roughly 93 million miles. Its surface area will be about 10,000 times greater than today. Its luminosity will be about 2,000 times greater. But despite this enormous increase in luminosity, the surface temperature will actually drop from about 5,500 degrees today to perhaps 3,000 degrees. This is because the same total energy is spread over a much larger surface area. Each square meter of surface radiates less intensely, but there are vastly more square meters. The sun will appear bloated and orange-red, filling the sky of any surviving inner planets. Let's talk about what happens to those planets. Mercury will be the first casualty. As the sun expands, Mercury's orbit will be engulfed. The tiny planet will be vaporized by the extreme heat and absorbed into the sun's outer layers. Venus will likely suffer the same fate. Its orbit lies about 67 million miles from the sun, well within the red giant's maximum extent. Earth's fate is less certain. When a star becomes a red giant, it also loses mass. The outer layers are only weakly bound by gravity, and stellar winds carry material away into space. A star might lose 30 to 40% of its mass during the red giant phase. As the sun loses mass, its gravitational pull weakens. Planets respond by drifting into wider orbits. The question is whether Earth's orbit will expand fast enough to outrun the advancing solar surface. Current models are roughly split. Earth might be swallowed by the expanding sun, or it might escape to a wider orbit, surviving as a planet but utterly transformed. Even if Earth avoids being engulfed, it won't be habitable. The increased luminosity will heat Earth's surface to thousands of degrees. Any remaining atmosphere will be blasted away by the intense solar wind. Earth will become a bare, scorched rock, perhaps still orbiting, but devoid of any trace of life. Mars will fare somewhat better, escaping engulfment with greater certainty. But it too will be dramatically heated. The outer solar system might become interesting during the red giant phase. Jupiter and Saturn will survive easily. Their moons, currently frozen solid, might thaw. Europa, Jupiter's ice-covered moon, is thought to have a liquid water ocean beneath its frozen surface. During the red giant phase, the increased solar luminosity might melt the ice. For a brief period, perhaps a few 100 million years, Europa could have an open ocean. Similar transformations might occur on other icy moons. Of course, the radiation environment would be harsh. The expanded sun would emit intense ultraviolet, and the solar wind would be much stronger. Life would need to remain underwater to survive, but the possibility is intriguing. Now let's look at what's happening inside the red giant sun. The helium core continues to contract and heat up. Eventually, it reaches a critical temperature, about 100 million degrees Celsius. At this temperature, helium nuclei can begin to fuse. Helium fusion proceeds through something called the triple alpha process. 3 helium nuclei, called alpha particles, collide and stick together to form a carbon nucleus. This is remarkable because it requires 3 particles to come together almost simultaneously, which is extremely rare. But at 100 million degrees, it happens often enough to power the star. But the helium flash, when helium fusion first ignites, is violent. The core of a red giant is strange. The electrons in the core are squeezed so tightly that they enter a quantum state called degeneracy. Degenerate matter doesn't behave normally. When you heat normal matter, it expands. But degenerate matter doesn't expand when heated. This means that when helium fusion ignites, there's no cooling feedback. The temperature rises, which increases the fusion rate, which raises the temperature further. The reaction runs away. The helium flash releases an enormous amount of energy in a very short time, perhaps just a few minutes. But here's the counterintuitive part. We wouldn't see it from outside. The energy is released in the core and is absorbed by the overlying layers before it can reach the surface. The sun will hiccup internally, but its external appearance won't change dramatically. After the helium flash, the core settles into stable helium fusion. The degeneracy is lifted because the core has expanded and heated enough to return to normal behavior. The sun enters a phase called the horizontal branch. During the horizontal branch, the sun will be smaller and hotter than during the red giant phase. It will fuse helium in its core and hydrogen in a surrounding shell. This phase lasts about 100 million years. But helium, like hydrogen, is a limited resource. Eventually, the core will run out of helium fuel. When that happens, the story repeats, but more dramatically. Helium fusion shifts to a shell surrounding an inert carbon-oxygen core. The outer layers expand again. The sun enters a second red giant phase, sometimes called the asymptotic giant branch. This second expansion is even more extreme. The sun might grow to 200 times its current radius. Its luminosity might reach 10,000 times its current value. And something else happens. The sun becomes unstable. Thermal pulses, caused by interactions between the helium-burning and hydrogen-burning shells, cause the sun's brightness to fluctuate. These pulses can be violent, each one blasting away more of the outer layers. The sun is beginning to shed its skin. Material carried away by stellar winds forms an expanding shell around the dying star. This shell contains elements created in the sun's interior, carbon and nitrogen and oxygen, dredged up by convection and now being released into space. The rate of mass loss accelerates. The sun might lose a significant fraction of its mass during the asymptotic giant branch phase, which lasts only about 1 million years. Notice the timescales. The main sequence lasts about 10 billion years. The first red giant phase lasts about 1 billion years. The horizontal branch lasts about 100 million years. The asymptotic giant branch lasts about 1 million years. Each phase is shorter than the last. The sun is accelerating toward its end. Within that final 1 million years, the sun will shed its outer layers entirely. The hot core will be exposed, and the dying star will create something beautiful. When astronomers first discovered planetary nebulae in the 18th century, they were puzzled. Through their primitive telescopes, these objects appeared as small, fuzzy disks, similar in appearance to the outer planets like Uranus and Neptune. Astronomers called them planetary nebulae because of this resemblance. The name stuck, even after we learned that these objects have nothing to do with planets. Planetary nebulae are the shed outer layers of dying stars, illuminated by the hot cores they left behind. They represent a brief but spectacular phase in stellar evolution. Let me describe what our sun's planetary nebula might look like. As the sun loses mass during the asymptotic giant branch, its outer layers expand outward into space. The material doesn't explode violently, like in a supernova. It drifts away, pushed by radiation pressure and stellar winds. The expanding material forms intricate structures. Some planetary nebulae are roughly spherical. Many have more complex shapes. Bipolar lobes extending in opposite directions, concentric rings suggesting multiple episodes of mass loss, jets and filaments and knots. The exact shape depends on factors we can't fully predict. The star's rotation, its magnetic field, whether it has a companion star that gravitationally influences the outflow. The Sun is a solitary star, but its rotation and magnetic field will leave their mark on the nebula. At the center of the expanding shell, the Sun's core is revealed. Stripped of its outer layers, the core is exposed to space. It's incredibly hot, perhaps 100,000 to 200,000 degrees at the surface. It's also incredibly small, only about the size of Earth despite containing roughly half the Sun's original mass. This hot, compact object is called a white dwarf, and its intense ultraviolet radiation ionizes the surrounding shell of gas, causing the atoms to glow. The nebula lights up in spectacular colors. Oxygen atoms emit a brilliant green. Hydrogen glows red and pink. Nitrogen contributes blue and purple. Helium adds its own hues. The overall effect is like a cosmic flower blooming in the darkness. We can observe thousands of planetary nebulae in our galaxy, each one unique. The Ring Nebula in Lyra is one of the most famous, appearing as a small, colorful ring with the white dwarf visible at its center. The Helix Nebula is one of the closest, its proximity making it appear relatively large in the sky. The Cat's Eye Nebula shows intricate nested shells and jets. The Butterfly Nebula has dramatic bipolar lobes extending from a central star, obscured by a disk of dust. When our Sun creates its planetary nebula, about 5 billion years from now, it will join this gallery. What shape will it take? We don't know, but it will be beautiful. The planetary nebula phase is brief by astronomical standards. The expanding shell moves outward at perhaps 10 to 20 miles per second. Over about 20,000 years, it spreads and thins. Eventually, the gas becomes too diffuse to glow visibly. The nebula fades, merging with the thin interstellar medium that pervades the galaxy. But the material doesn't disappear. It becomes part of the raw material for future generations of stars and planets. This is the Sun's gift to the cosmos. During its lifetime, the Sun created helium from hydrogen. During the red giant phases, it created carbon and oxygen from helium. Through a process called dredge-up, convection mixed these heavier elements into the outer layers. Now those layers are being released into space. The carbon in future organic molecules, the oxygen in future water, the nitrogen in future atmospheres. All of these might trace their origins to our Sun. This is cosmic recycling on the grandest scale. Stars are born from clouds of gas. They live. They create heavier elements through fusion. They die and return those elements to space. New stars form from the enriched material. The cycle continues, each generation of stars richer in heavy elements than the last. Our Sun is a third-generation star. The first generation, born from the pure hydrogen and helium of the Big Bang, created the first heavy elements. When those stars died, second-generation stars formed from the enriched material. Our Sun formed from material that had passed through two previous stellar generations. The atoms in your body have already had cosmic adventures. The carbon in your cells was forged in an ancient star. The oxygen you're breathing was created through nuclear fusion billions of years ago. When our Sun dies, its material will continue this journey, perhaps becoming part of new worlds and new forms of life billions of years from now. Now let's turn our attention to what remains at the center of the expanding nebula, the white dwarf Sun. This object is extraordinary. It contains about half the Sun's original mass, but squeezed into a volume about the size of Earth. The density is almost inconceivable. A teaspoon of white dwarf material would weigh about 15 tons. The gravitational pull at the surface is about 350,000 times stronger than Earth's gravity. If you could somehow stand on a white dwarf, you would be crushed instantly. What keeps the white dwarf from collapsing further? Not fusion. Fusion has stopped. There's no energy source pushing back against gravity. Instead, the white dwarf is supported by something called electron degeneracy pressure. At the extreme densities inside a white dwarf, electrons are squeezed so close together that quantum mechanics takes over. A principle called the Pauli exclusion principle prevents electrons from occupying the same quantum state. This creates an outward pressure that resists further compression. This isn't thermal pressure, which comes from heat. Electron degeneracy pressure is a quantum mechanical effect that would exist even at absolute zero. It's what keeps white dwarfs stable, but stable doesn't mean unchanging. White dwarfs don't generate energy. They're like embers pulled from a fire, glowing with residual heat, but slowly cooling. Over time, they radiate their thermal energy into space. The cooling is incredibly slow. White dwarfs have small surface areas, which limits how fast they can radiate, and they have enormous amounts of stored thermal energy. A newly formed white dwarf, freshly exposed after shedding its envelope, might have a surface temperature of 100,000 degrees or more. It glows blue-white, brilliant and fierce. Over billions of years, it cools. From blue-white to yellow, to orange to red. Each stage takes longer than the last, because cooler objects radiate less energy. After about 10 billion years, a white dwarf will have cooled to perhaps 5,000 or 6,000 degrees, roughly the current temperature of the Sun's surface. But because of its tiny size, it will be incredibly dim. After 100 billion years, it will have cooled further, perhaps to just a few hundred degrees above absolute zero. It will emit almost no visible light, only dim infrared radiation. And eventually, after trillions of years, the white dwarf will approach absolute zero. It will become what's called a black dwarf, a cold, dark remnant of a once brilliant star. No black dwarfs exist yet. The universe is only 13.8 billion years old, and even the oldest white dwarfs haven't had time to cool significantly. Black dwarfs are purely theoretical, predicted by physics, but never observed. Our Sun's ultimate fate, its transformation into a black dwarf, lies in a future so distant and it's almost meaningless to contemplate. Trillions of years, 1,000 times longer than the current age of the universe. Let's pause and consider what the solar system will look like during this endless twilight. The planetary nebula is long gone, dispersed into interstellar space. The white dwarf glows dimly at the center of the system, providing almost no warmth. What planets remain? Mars, probably. Jupiter and Saturn, certainly. Uranus and Neptune. The Kuiper Belt objects, including Pluto. All of these will have survived the red giant phases, but they orbit in expanded orbits now because the sun lost so much mass, and they're cold, incredibly cold. Jupiter receives only about 4% as much solar energy as Earth does today. When the sun becomes a white dwarf, that will drop by another factor of thousands or millions. The outer planets will approach the temperature of interstellar space, just a few degrees above absolute zero. For trillions of years, this frozen remnant of the solar system will drift through the galaxy. The white dwarf will slowly cool. The planets will continue their silent orbits. Nothing will change. And then, finally, the white dwarf will cool to absolute zero. A black dwarf, surrounded by frozen worlds, drifting through empty space. This is how the solar system ends. Not with a bang, but with an infinitely slow fade into darkness. Throughout this journey, we focused on our sun as an individual, but our sun is not alone. It's one of perhaps 400 billion stars in the Milky Way galaxy, and the Milky Way is one of 2 trillion galaxies in the observable universe. Let's place our sun in this cosmic context. As we've discussed, the sun is a G-type main sequence star, often called a yellow dwarf. But despite the name, the sun is actually larger and brighter than about 85% of stars in the galaxy. The most common stars are red dwarfs, also called M-type stars. These small, cool stars make up about 75% of all stars. They're so dim that not a single red dwarf is visible to the naked eye from Earth, even though the nearest star system, Alpha Centauri, includes a red dwarf called Proxima Centauri, just 4.2 light years away. Red dwarfs have masses ranging from about 8% to 50% of the sun's mass. Their low mass means their cores are cooler, and fusion proceeds more slowly. This gives them incredibly long lifespans. A red dwarf with 10% of the sun's mass will burn for about 10 trillion years. That's 1,000 times longer than the sun will last. Every red dwarf that has ever formed is still burning today and will continue for an almost inconceivable span of future time. These tiny stars will be the last lights in the universe. Long after the sun has become a black dwarf, long after all sun-like stars have died, red dwarfs will still be shining. On the other end of the spectrum are the massive stars, with more than about 8 solar masses. These are the rare blue giants and supergiants that dominate the night sky, despite making up less than 1% of all stars. Massive stars burn bright and die young. A star with 50 solar masses might live only a few million years. They're so short-lived that a massive star born when dinosaurs first appeared would have died long before the dinosaurs went extinct. And when massive stars die, they don't become white dwarfs. They're too heavy. The white dwarf fate requires a core less than about 1.4 solar masses. This limit was calculated by the physicist Subrahmanyan Chandrasekhar and is called the Chandrasekhar limit. At this mass, the inward pull of gravity overwhelms electron degeneracy pressure. The core cannot support itself as a white dwarf. For stars with initial masses between about 8 and 25 solar masses, the core collapses beyond the white dwarf stage. Electrons are forced to merge with protons, creating neutrons. The core becomes a neutron star, an object so dense that a teaspoon would weigh about 1 billion tons. Neutron stars are only about 12 miles across, the size of a city, yet they contain more mass than the Sun. They spin rapidly, sometimes hundreds of times per second, and emit beams of radiation from their magnetic poles. When these beams sweep past Earth, we see pulses of radio waves or X-rays. These are called pulsars. For the most massive stars, even neutron degeneracy pressure cannot halt the collapse. The core keeps falling inward, past the neutron star stage, until it forms a black hole. A region of space where gravity is so intense that nothing, not even light, can escape. Our Sun will never become a neutron star or black hole. It's simply not massive enough. The Chandrasekhar limit ensures that our Sun's core will stabilize as a white dwarf, supported by electron degeneracy pressure. But understanding these more extreme fates helps us appreciate where our Sun fits in the grand scheme of stellar evolution. Let me tell you about a peculiar category of stars that might seem familiar. Stars with planetary systems. For most of human history, we didn't know whether other stars had planets. The Sun was the only star we knew to host a planetary system. Maybe it was unique. Maybe planets were rare. In 1992, astronomers discovered the first confirmed exoplanets, orbiting a pulsar of all things. These were strange worlds in a strange place, probably formed from debris after the supernova explosion that created the pulsar. In 1995, the first exoplanet around a Sun-like star was discovered. 51 Pegasi b is a gas giant orbiting incredibly close to its star, completing an orbit in just 4 days. This hot Jupiter was nothing like what scientists expected to find. Since then, the floodgates have opened. As of now, we've confirmed over 5,500 exoplanets, with thousands more candidates awaiting confirmation. And the Kepler Space Telescope's data suggests that virtually every star in the galaxy has at least one planet. Planets are not rare. They're ubiquitous. This has profound implications for understanding our own solar system. The Sun is not special in having planets. What might be special is the particular arrangement of our planets, with small rocky worlds close in and gas giants farther out. Many exoplanetary systems have very different architectures. But let's return to our Sun's specific fate and consider one more aspect of stellar evolution: binary stars. About half of all Sun-like stars exist in binary or multiple star systems. 2 or more stars orbiting each other, gravitationally bound. Our Sun is a loner. It has no stellar companion. This might be fortunate for the development of stable planetary orbits and life. Binary stars can gravitationally perturb planets, potentially ejecting them from the system or sending them crashing into the stars. But being alone also means our sun will evolve in isolation. It won't exchange mass with a companion. It won't merge with another star. Its fate is sealed. Main sequence, red giant, planetary nebula, white dwarf, black dwarf. Binary stars can have more dramatic fates. In some systems, a white dwarf orbits close to a normal star. Gas from the normal star can flow onto the white dwarf, accumulating on its surface. When enough material accumulates, it can ignite in a thermonuclear explosion called a nova. If mass transfer continues, the white dwarf can be pushed over the Chandrasekhar limit. At this point, the entire white dwarf detonates in a Type Ia supernova, one of the most powerful explosions in the universe. The white dwarf is completely destroyed, leaving behind no remnant. Our solitary sun will avoid these violent scenarios. It will die quietly, alone, fading into eternal darkness. Now let's consider a question that might have been nagging at you. We've talked about what will happen to the sun, but what about us? Not humanity specifically. We'll be long gone before the sun becomes a red giant. Our species is unlikely to last even another 1,000,000 years in its current form. Whether we go extinct, evolve into something else, or merge with technology. But what about intelligent life in general? What about any descendants, biological or artificial, that might carry on our legacy? The death of the sun, while devastating for Earth, is a local event. It affects only our solar system. Other star systems will be fine. And intelligent beings, if they still exist 5 billion years from now, will surely have spread beyond Earth. In fact, even with current technology concepts, we could imagine interstellar travel taking centuries or millennia. In 1 billion years, our descendants could have colonized the entire galaxy. For any civilization that survives that long, the death of one star, even their home star, would be merely a local concern. They might even have the technology to mitigate it. Could you move a planet to a safer orbit? Could you engineer the sun itself, somehow extending its life? These ideas seem like fantasy now, but 1 billion years is a long time for technological development. Or perhaps future beings won't care about individual stars at all. They might live in artificial habitats, harvesting energy from any available source. They might have transcended physical form entirely, existing as patterns of information in computational substrates. The death of the sun would be historically significant, a milestone marking the end of humanity's birthplace. But it wouldn't be the end of everything. Let's zoom out even further. What happens to all the stars in the universe? The sun's life cycle is echoed with variations by every star in the cosmos. All stars are born from collapsing clouds. All stars shine through nuclear fusion. All stars eventually exhaust their fuel and die. But the universe has a schedule. Star formation won't continue forever. The raw material for stars, the hydrogen and helium gas that fills molecular clouds, is finite. Every time a star forms, it removes gas from the interstellar medium. Some of that gas is returned when the star dies, but not all of it. Heavy elements locked in white dwarfs and neutron stars and black holes are removed from circulation. The rate of star formation in the universe peaked about 10 billion years ago, around the time our sun was born. Since then, it's been declining. The universe is using up its star-forming material. Current estimates suggest that star formation will continue for another 100 trillion years or so, but at ever-decreasing rates. Eventually, the last stars will form, and then no more. Let's fast forward to that distant era. 100 trillion years from now, the universe is very different. All massive stars are long dead. They lived fast and died young, exploding as supernova within the first few billion years of the universe's history. All sun-like stars are dead. Our own sun became a black dwarf roughly 10 trillion years ago, and it's not alone. Every yellow dwarf, every orange dwarf, has followed the same path. Only red dwarfs remain. These tiny dim stars were always the most numerous, and their incredibly long lifespans mean they're the last survivors. The red dwarfs that formed shortly after the Big Bang are still burning, still fusing hydrogen into helium at their leisurely pace. The universe is dark. Galaxies are populated by cooling white dwarfs, ancient neutron stars, black holes, and the dim red embers of the last surviving stars. New stars no longer form. The raw material is exhausted. The night sky, if anyone were there to see it, would be nearly black. The only visible stars would be the red dwarfs, and they're so dim you'd need to be quite close to see them. But even red dwarfs have limits. Even they will eventually burn out. The last red dwarf will exhaust its hydrogen fuel in about 100 trillion years, more or less. When it does, it too will become a white dwarf, then slowly cool toward a black dwarf. After the last red dwarf dies, the stellar era is over. No new stars will ever form. The only objects in the universe will be stellar remnants. White dwarfs, neutron stars, and black holes, plus planets, asteroids, and other debris still orbiting their dead stellar hosts. This is called the degenerate era. Degenerate not in a moral sense, but in a physics sense, referring to the degenerate matter that makes up white dwarfs and neutron stars. During the degenerate era, the universe is dark and cold, but it's not static. Things still happen, just very slowly. White dwarfs continue to cool, asymptotically approaching absolute zero. This takes an almost inconceivable time. After 10 to the power of 15 years, about 10 times longer than the current age of the universe, white dwarfs will still be relatively warm. After 10 to the 17 years, they'll have cooled significantly. Complete cooling to true black dwarf status takes something like 10 to the 25 years or more. Meanwhile, galaxies slowly dissolve. Stars and the objects that were once stars occasionally pass close to each other. Gravitational interactions can eject some objects into intergalactic space, while others fall toward the galactic center. Over vast timescales, galaxies shed most of their mass, with the remainder concentrating around the central black hole. These central black holes grow by consuming nearby matter, but even they are not eternal. In 1974, Stephen Hawking made a remarkable theoretical discovery. Black holes are not truly black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation carries energy away from the black hole. And since mass and energy are equivalent, the black hole loses mass over time. Eventually, it evaporates completely. For stellar mass black holes, this process takes about 10 to the 67 years. For the supermassive black holes at galactic centers, containing billions of solar masses, it takes about 10 to the 100 years. Let me try to convey how long that is. If you wrote a 1 followed by 100 zeros, that's the approximate number of years before the largest black holes evaporate. The current age of the universe, 13.8 billion years, is only about 10 to the 10 years. The evaporation time for supermassive black holes is inconceivably longer. When the last black hole finally evaporates, the black hole era ends. What remains? A universe of elementary particles, scattered so thin that they almost never interact. Photons, neutrinos, electrons, positrons, perhaps some protons and neutrons, though even these might decay over sufficiently long timescales if certain theories are correct. No stars, no planets, no structures of any kind, just particles drifting through an ever-expanding void, growing ever more sparse as the universe continues to expand. This is the heat death of the universe. Not a death by fire, but a death by cold. Not a dramatic ending, but an eternal, changeless twilight. Is this depressing? Perhaps. But let me offer a different perspective. The heat death is unimaginably far in the future. The universe is only 13.8 billion years old. The stellar era, when stars shine and life is possible, will last perhaps 100 trillion years. We're at the very beginning. Our sun's life, from birth to death, is a tiny slice of cosmic history. But within that slice, remarkable things happen. Hydrogen clouds collapse into stars. Stars forge heavy elements. Planets form. Life emerges. Intelligence arises. Beings look up at the sky and wonder. The universe is not just matter and energy. It's also patterns and processes and experiences. And those things matter, even if they're temporary. Everything ends eventually. Stars, galaxies, the universe itself. But that doesn't diminish what happens along the way. We've traveled an incredible distance together. We started 5 billion years in the past, watching a cloud of gas collapse under its own gravity. We witnessed the birth of a protostar, the ignition of nuclear fusion, the stabilization of a young sun. We explored the sun as it is today, its layered structure, its nuclear heart, its dynamic surface. We marveled at sunspots and flares and coronal mass ejections. We learned about the solar cycle and the mysteries of coronal heating. We looked ahead 5 billion years, watching the sun swell into a red giant, shed its outer layers, expose its white dwarf core. We followed that core as it cooled over trillions of years, eventually becoming a black dwarf in the endless night. And we placed our sun's story within the larger context of stellar evolution and cosmic history. From the birth of the first stars to the eventual heat death of the universe. What does it all mean? Let me share some reflections. First, we are stardust. This is not poetry, it's literal truth. Every atom of carbon in your body was forged in a star. Every atom of oxygen you breathe came from stellar fusion. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all of it was created inside stars and scattered into space when those stars died. The sun is continuing this process. Right now, it's creating helium from hydrogen. Billions of years from now, it will create carbon and oxygen from helium. When it dies, it will release these elements into space, where they might someday become part of new stars, new planets, new life. We are connected to every star in the universe through this cycle of stellar birth, life, death, and rebirth. We are part of something vast and ongoing. Second, the sun gives us perspective on time. Human civilization is about 10,000 years old. The sun has been burning for 4.5 billion years. That ratio is like comparing 1 second to 14 years. Everything we've ever done, every empire that has risen and fallen, every idea that has been thought, every life that has been lived, has happened in a cosmic eye blink. The sun barely noticed. And yet, the sun's life itself is brief compared to the age of the universe, which is brief compared to the eons remaining before the last stars die. Time stretches out before us and behind us in quantities that the human mind cannot truly grasp. This perspective can be humbling. It can also be liberating. Our individual worries and conflicts seem small against the backdrop of cosmic time. And yet, we're the ones asking these questions. In all the vastness of space and time, conscious beings have emerged who can contemplate the life and death of stars. Third, the sun reveals the power of physics. Everything we've discussed, the fusion reactions in the core, the balance of gravity and pressure, the quantum mechanics of electron degeneracy, the incredible timescales of stellar evolution, all of this is predicted by physical laws that humans discovered over the past few centuries. Newton's law of gravity, Einstein's equation relating mass and energy, the quantum principles that govern atomic and subatomic behavior. These laws, expressed in mathematical form, allow us to predict what happens inside a star, even though we've never visited one. This is remarkable. The universe operates according to principles that are comprehensible to human minds. We're not just observers of the cosmos. We're beginning to understand it. Fourth, the sun reminds us that everything changes. Nothing lasts forever. Stars are born, they shine for a while, and then they die. This is true for red dwarfs that burn for 10 trillion years, and for massive blue giants that burn for 10 billion years. It's true for our sun. Change is built into the fabric of reality. Fighting it is futile. The question is what we do with the time we have. The sun has been stable for 4.5 billion years and will remain stable for another billion or so. That's our window. 1 billion years of habitable Earth. 1 billion years for life to flourish, for intelligence to emerge, and perhaps spread beyond its birthplace. What happens after that is beyond our ability to influence, at least for now. But what happens within that window is up to us and our descendants, whatever form they take. Fifth, The sun connects us to the rest of humanity. Every human being who has ever lived has been warmed by the same sun. Ancient ancestors on the African savanna, pharaohs in Egypt, philosophers in Greece, farmers in China, explorers crossing oceans, scientists unraveling cosmic mysteries. The same fusion reactions that warmed a dinosaur 100 million years ago are warming you today. The sun is our common heritage, the one thing that all humans in all times and places share. When you watch a sunset, you're sharing an experience with every human who has ever watched a sunset. There's something profound about that connection. Sixth and finally, the sun invites wonder. We've explained a lot in this video. We've talked about fusion reactions and stellar evolution, and the physics of degenerate matter. But explaining something doesn't diminish it. If anything, understanding enhances wonder. Knowing how the sun works makes it more impressive, not less. The fact that we live next to a nuclear furnace that's been burning steadily for 4.5 billion years, powered by reactions we can describe mathematically, producing the light and warmth that makes all life possible. That's incredible. The universe is under no obligation to be comprehensible, and yet it is. The universe is under no obligation to be beautiful, and yet it is. The universe is under no obligation to produce conscious beings who can appreciate its wonders, and yet it did. We are the cosmos contemplating itself. In our curiosity about the sun is learning about itself through us. I don't know if that has any ultimate meaning, but it feels meaningful. It feels like a gift. Before we conclude, let's turn our gaze towards something more immediate than the sun's death 5 billion years from now. Let's talk about what the sun means for humanity's future in the coming centuries and millennia. The sun is not just an object of scientific fascination. It's the energy source that powers our entire civilization. Every watt of solar energy that hits Earth's surface, every gust of wind generated by differential solar heating, every drop of rain that fills our hydroelectric dams, every fossil fuel that stores ancient sunlight captured by plants millions of years ago, all of it traces back to the sun. We are utterly dependent on our star. And as we face the challenges of the 21st century, particularly climate change and resource depletion, the sun offers solutions. Solar power has become one of the fastest growing energy sources on Earth. The efficiency of solar panels has increased dramatically, while costs have plummeted. In many parts of the world, solar electricity is now cheaper than fossil fuels. This makes sense when you consider the numbers. The sun delivers about 174 petawatts of power to Earth's upper atmosphere. After reflection and absorption, about 89 petawatts reach the surface. Humanity's total energy consumption is about 18 terawatts. The sun delivers nearly 5,000 times as much energy as we use. We're only scratching the surface of this potential. But even ground-based solar has limits. Weather, night, seasons. The best solar resources are often in deserts, far from population centers. Some visionaries have proposed space-based solar power. Giant solar collectors in orbit, where the sun always shines, beaming energy down to Earth via microwaves or lasers. This idea has been around since the 1970s, but has remained impractical due to the cost of launching material into space. That might be changing. New rocket technologies are driving down launch costs. Some companies are seriously studying space-based solar power for the 2030s or 2040s. Even more ambitious is the concept of a Dyson sphere, or more practically, a Dyson swarm. This is a hypothetical megastructure that would capture a significant fraction of a star's total energy output. Instead of a solid shell around the sun, which would be impossible to build, a Dyson swarm would consist of millions or billions of individual collectors orbiting the sun. Together, they would capture and utilize vastly more energy than any planet-based system. A civilization that built a Dyson swarm around the sun would have access to about 384 trillion terawatts of power. That's 20 billion times humanity's current energy consumption. This much energy could power almost anything imaginable: interstellar spacecraft, massive computational systems, terraforming projects, things we haven't even thought of yet. Building a Dyson swarm is far beyond our current capabilities. It would require mining asteroids for materials, developing self-replicating manufacturing systems, and coordinating a project of unprecedented scale. But there's no physical law that says it's impossible. If humanity survives for another few thousand years and continues to develop technologically, structures like this might become feasible. The sun is an enormous resource, and we've barely begun to tap it. Now let's consider a different aspect of the sun's future relevance: space weather. As we discussed earlier, the sun is not a steady, unchanging object. It has cycles of activity, with periods of more and fewer sunspots, flares, and coronal mass ejections. These space weather events can affect Earth. In the modern world, with our increasing dependence on technology, space weather has become a serious concern. Solar flares can disrupt radio communications and GPS signals. Coronal mass ejections can trigger geomagnetic storms that damage satellites, disrupt power grids, and create beautiful auroras. The Carrington event of 1859 was the most powerful geomagnetic storm on record. If a similar event occurred today, the damage could be catastrophic. Estimates suggest it could cause trillions of dollars in damage and take years to fully recover from. Space agencies now monitor the sun continuously, watching for dangerous activity. Satellites like the Solar Dynamics Observatory and the Parker Solar Probe are helping us understand and predict space weather. But our ability to predict solar events is still limited. We can see a CME leaving the sun and estimate when it will arrive at Earth, typically 1 to 3 days later. But we often can't predict how strong its effects will be until it actually hits. Improving space weather prediction is an active area of research. It's not just a scientific curiosity. It's a matter of protecting our technological civilization. There's another sense in which the sun shapes our future: the search for life beyond Earth. When we look for potentially habitable exoplanets, we often focus on the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. This zone depends on the star's luminosity. For sun-like stars, the habitable zone is at about the right distance to receive a familiar amount of warmth. Planets in the habitable zones of sun-like stars are particularly interesting targets for the search for life. But we've also found potentially habitable planets around red dwarf stars, like the TRAPPIST-1 system and Proxima Centauri b. These planets orbit much closer to their stars because red dwarfs are so dim. Whether such planets can actually support life is debated. Red dwarfs have violent flares that could strip away atmospheres. Planets so close might be tidally locked, with one side always facing the star. Our own Sun, a G-type star, might represent a sweet spot for the development of complex life. Or maybe we're biased because it's the only example we know. Finding life around other types of stars would help us understand how special our situation really is. The sun has also shaped our culture in profound ways. From the earliest sun worship religions to modern solar science, the sun has been central to human thought. Holidays around the solstices, calendars based on the solar year, myths and stories about the day star. Even our sense of time is tied to the sun, the day, the year. These fundamental units are based on Earth's rotation and orbit relative to the sun. Our circadian rhythms are tuned to the 24-hour day. As we venture into space, we'll carry these solar influences with us. Even on Mars, where the day is slightly longer, human settlers will probably try to maintain something like an Earth Day rhythm. The sun has shaped our biology and our culture in ways that will persist long after we leave our home planet. Let me tell you about a moment that changed how I think about the sun. It was an ordinary morning. I was drinking coffee, looking out the window, and the sun was just rising. Golden light was streaming through the trees, casting long shadows across the grass. And suddenly, I really saw it. That light had started as gamma rays in the core of the sun, created by nuclear fusion reactions 170,000 years ago. It had spent all that time bouncing through the radiative zone, gradually diffusing outward. Then it had traveled through space for 8 minutes to reach Earth, and now it was warming my face. I was bathed in ancient light, created before humans existed, reaching me at that exact moment because of the precise geometry of the cosmos. This was not new information. I knew the science, but in that moment, knowledge became experience. I felt connected to something vast. This is what understanding can do. It doesn't diminish wonder. It deepens it. The sun is not just a ball of hot gas. It's a story 4.5 billion years in the telling. It's a promise of 5 billion more years of warmth. It's a connection to every other star in the universe, all governed by the same physics. When you understand what the sun is and how it works, ordinary moments become extraordinary. A sunrise is a glimpse of nuclear physics. A sunset is a meditation on celestial mechanics. A sunbeam through a window is the end point of a journey that started before your species evolved. I think this is why we study the cosmos, not just for practical applications, though those are valuable, not just for intellectual satisfaction, though that's real, but for transformation, for the expansion of perspective, for the sense of participating in something larger than ourselves. The sun has been the center of human experience for all of history. It determined when we woke and when we slept. It governed the growing seasons that fed us. It was worshipped as a god by cultures around the world. Now we understand it as a natural object, following physical laws, destined to evolve and eventually die. This is not a demotion, it's an elevation. The sun's significance doesn't depend on its being divine. It depends on its being what it is, a star. And what is a star? A place where atoms fuse and light is born. A furnace that burns for billions of years. A beacon visible across interstellar distances. A giver of life to any planet fortunate enough to orbit in the right place. The sun is all of these things. And so is every star you see in the night sky. When you look up at the stars, you're looking at other suns. Some are much larger and brighter than ours. Some are smaller and dimmer. Some are young, still surrounded by the dust from which their planets are forming. Some are old, swelling into red giants or contracting into white dwarfs. Each one is a nuclear furnace. Each one might have planets. Some of those planets might have life. We don't know yet how common life is in the universe. We don't know if intelligence is rare or ubiquitous. These are questions for the coming decades as we develop better telescopes and techniques for studying exoplanets. But we know that life is possible. We know it because we're here. We know it because the sun made Earth habitable and life emerged. If it happened here, why not elsewhere? The universe is vast beyond comprehension. There are more stars in the observable universe than grains of sand on all the beaches of Earth. The odds that our sun is the only one to host life seem vanishingly small. And yet, we have no proof. The search continues. This is one of the great questions of our time. Are we alone? Is the universe teeming with life? Or is it a vast, sterile emptiness broken only by our tiny oasis? The sun can't answer this question for us, but it provides the example. It shows us what a life-bearing star looks like. It gives us a template for the search. Every sun-like star we find, every planet in a habitable zone, is a potential answer. And every answer, whether life is found or not, tells us something about our place in the cosmos. Now we come to the heart of everything we've discussed, the profound truth that lies at the center of our sun's story. The sun is going to die, this is certain. It's written in the laws of physics. The hydrogen fuel in the core is finite. Fusion will eventually cease. The sun will expand, shed its outer layers, and collapse into a white dwarf. Over trillions of years, that white dwarf will cool into a black dwarf. The light that has warmed Earth for billions of years will go out forever. This sounds like tragedy. The end of our star, the death of our solar system. But here's what I want you to understand. The death of the sun is not just an ending. It's a transformation. It's a gift. When the sun dies, it will return most of its material to the cosmos. The helium created from hydrogen. The carbon and oxygen created from helium. The nitrogen and other elements dredged up from the interior. This material will spread into interstellar space. It will mix with the gas already there. It will become part of molecular clouds, the stellar nurseries where new stars are born. Someday, perhaps billions of years from now, a new star will form from a cloud that contains atoms from our sun. And that new star might have planets. And those planets might develop life. The sun's death is the beginning of something new. This is not speculation. This is how the universe works. We see it happening now. Stars are constantly dying and being born. The heavy elements that make planets and life possible were all created in stars and distributed by stellar death. Our own sun, our own Earth, our own bodies are made from the remnants of stars that died billions of years ago. We are recycled stardust, and when the sun dies, its material will be recycled in turn. The philosopher Alan Watts once said that we are the universe experiencing itself. The atoms in your body have been many things: parts of stars, parts of planets, parts of countless organisms. And they will be many things again after you're gone. You are not separate from the cosmos. You are the cosmos, temporarily organized into a particular pattern. When that pattern dissolves, the matter and energy continue. Nothing is truly lost. The same is true of the sun. It's not a permanent fixture of the sky. It's a process, a temporary pattern of matter and energy. It formed, it shines, it will die. But the matter and energy will continue. This is the gift of mortality. It enables change. It enables new patterns to emerge. If nothing ever died, nothing could be born. A universe of immortal stars would be a static universe. A universe of mortal stars is a dynamic universe, constantly creating and destroying, endlessly generating novelty. We are part of this dance. Our brief lives are contributions to a cosmic story that stretches from the Big Bang to the heat death and perhaps beyond. Does this provide comfort? That depends on you. Some find it cold and impersonal. Others find it deeply meaningful. For me, there's something beautiful about being temporary. It makes each moment precious. It connects us to everything else that is also temporary, which is everything. The sun will die, but first it will shine for another 5 billion years. That's an almost incomprehensible amount of time. Time enough for life on Earth to evolve in ways we can't predict. Time enough for intelligence to spread through the solar system and perhaps beyond. Time enough for wonders we can't imagine. And when the sun does die, whenever conscious beings exist in that distant future, we'll witness something spectacular. The swelling red giant blazing across the sky. The shed envelope creating a planetary nebula of extraordinary beauty. The exposed white dwarf glowing blue-white before beginning its long cooling. They will watch our sun's transformation, knowing that the atoms being released will become part of future stars and planets, and perhaps future living beings. That's not an ending. That's a beginning. The sun's death is a gift to the future. Everything it has created, including us, is a gift to the present. And the understanding we've gained, the science that reveals the sun's true nature, is a gift to ourselves. We are the first generation of humans who truly understand the sun. For all of history, the sun was a mystery, a god, an inexplicable fire in the sky. Now we know what it is. A main sequence star, a nuclear fusion reactor, a cosmic object with a past, a present, and a future that we can trace with remarkable precision. This knowledge is precious. It connects us to the universe in ways our ancestors couldn't imagine. It reveals our true cosmic heritage. We are children of the sun, not metaphorically, but literally. Everything we are comes from solar energy, and we are made of atoms that were once part of stars like our sun. This is the profound truth at the heart of stellar astronomy. We belong to the cosmos. We are not visitors here. We are part of the process that creates suns and planets and life and consciousness. The sun's story is our story. Its birth, its life, its eventual death. We share this narrative with our star. And just as the sun will leave behind material for future generations of stars, we too can leave something behind. Knowledge, culture, perhaps descendants who will carry on after we're gone. The universe is not indifferent to us. We are the universe becoming aware of itself. In studying the sun, we are the sun coming to understand its own nature. This is remarkable. This is precious. This is worth celebrating. We've reached the end of our journey. We started 4.6 billion years ago, watching a cloud of gas collapse into a protostar. We followed the ignition of fusion, the stabilization of the main sequence, the slow changes that have brought the sun to its current state. We explored the sun's interior, from the nuclear furnace of the core to the bubbling convection of the outer layers. We watched sunspots and flares and coronal mass ejections. We puzzled over the mystery of the hot corona. We looked ahead, watching the sun swell into a red giant that will transform the inner solar system. We saw the planetary nebula that will spread the sun's material across light years of space. We followed the white dwarf remnant as it cooled over trillions of years toward its final state as a black dwarf. We placed our sun's story in context, comparing it to other stars, other fates. We traced the ultimate destiny of all stars, from the last red dwarfs to the evaporating black holes. And we reflected on what it all means, the cosmic connections, the perspective on time, the wonder of understanding. Let me summarize the key points we've covered. The sun formed 4.6 billion years ago from a collapsing cloud of gas and dust. It ignited nuclear fusion and has been burning steadily ever since. The sun converts about 4 million tons of matter into energy every second through the fusion of hydrogen into helium. This energy keeps the sun stable against gravitational collapse. The sun is currently in the main sequence phase of its life, which will last another 5 billion years or so. During this time, it is slowly brightening, which will eventually make Earth uninhabitable. When the core hydrogen is exhausted, the sun will become a red giant, swelling to engulf Mercury and Venus, and possibly Earth. It will then shed its outer layers, creating a planetary nebula, and collapse into a white dwarf. The white dwarf will cool over trillions of years, eventually becoming a black dwarf, a cold, dark remnant of the once brilliant star. The sun's material, released during the red giant and planetary nebula phases, will become part of future generations of stars and planets. We are connected to the sun and to all stars through the cosmic cycle of stellar birth, life, death, and rebirth. The atoms in our bodies were forged in ancient stars. These are the facts. But facts alone don't capture the significance. The sun is our home star. It has nurtured life on Earth for billions of years. It will continue to shine, stable and reliable for billions more. We are extraordinarily fortunate to live in this cosmic moment. Understanding the sun deepens our appreciation of it. Every sunrise becomes a reminder of nuclear physics. Every sunset becomes a meditation on celestial mechanics. Every moment of warmth is a gift for a process that began 4.6 billion years ago. I hope this video has changed how you see the sun. I hope it has given you a sense of connection to the cosmos. I hope it has sparked curiosity that will stay with you long after the video ends. And now, I have a request. If you've made it this far, you're clearly someone who cares about these big questions. Someone who wants to understand the universe. Someone who finds wonder in the workings of nature. Please subscribe to the channel if you haven't already. We explore mysteries like this regularly, from the nature of black holes to the possibility of life beyond Earth. Each video is a journey into the unknown, guided by the best science available. Hit the bell icon so you'll be notified when new videos come out. YouTube's algorithm is mysterious, and notifications ensure you won't miss anything. And leave a comment below. I'd love to hear your thoughts. What struck you most about the sun's life cycle? What questions do you still have? What topics would you like to see explored in future videos? Your engagement helps the channel grow. It lets me know that people care about these topics. It motivates me to keep creating. If you found value in this video, consider sharing it with someone who might enjoy it. Space enthusiasts, science lovers, anyone curious about our place in the cosmos. Thank you for spending this time with me. Thank you for your curiosity. Thank you for being part of this community of wonder seekers. Until next time, keep looking up. The universe is waiting to be understood. Before we part, let me leave you with one last thought. Right now, as you watch this, the sun is shining. If it's daytime where you are, you can feel its warmth. If it's night, you're on the side of Earth facing away from it. But the sun is still there, still burning, still sending its light across 93 million miles of space. That light left the sun about 8 minutes ago. But the energy that created that light, the fusion reactions in the core, happened 170,000 years ago. When those photons began their journey through the radiative zone, there were no modern humans. Our species hadn't evolved yet. Now those ancient photons are reaching us, warming our skin, enabling photosynthesis, powering our civilization. This will continue for another 5 billion years. The sun will keep burning. The light will keep coming. Earth will remain habitable for about 1 billion of those years. That's an almost inconceivable amount of time. More than 1 billion years of sunrises and sunsets. 1 billion years of summer and winter. 1 billion years of life flourishing on this small blue planet. And then, slowly, things will change. The sun will brighten. The earth will warm. The oceans will evaporate. Life as we know it will become impossible. But by then, humanity, or whatever we've become, will have had plenty of time to adapt, to migrate, to spread beyond Earth, to become something we can barely imagine. The sun's death is not our death if we play our cards right. It's just the end of one chapter. And when the sun does finally become a red giant, swelling out to engulf the inner planets, it will be creating something beautiful. The planetary nebula will glow in colors we've seen in countless telescope images. It will be a memorial to everything that happened here. To life, to us. Someday, perhaps, intelligent beings around a distant star will point their telescopes at our region of the galaxy and see a faint planetary nebula. They won't know its history. They won't know that a small blue planet once orbited there, a planet that teemed with life, a planet that produced beings who wondered about the stars. But we know. We're here now, in the brief window when humans exist and Earth is habitable and the sun is stable. We're the witnesses. Let's make it count. Go outside sometime soon. Look at the sun, carefully, without staring directly at it. Feel its warmth on your skin. Remember what you've learned. That light is ancient. That warmth is nuclear. That star is your home. And for a few more billion years, it will continue to shine, stable and generous, asking nothing in return. That's the sun. That's our star. And that's something worth knowing.